So, good morning all. Good morning all. Hope you can hear me okay. Welcome to today's webinar. First of all, I think it's good to see we've got excellent attendance, so thank you for joining. Just to introduce myself, I am Peter Skanes. I'm the Program Manager for IDE, the Institute of Engineering, and if you're not familiar with who we are, then we have quite a wide-ranging role. So essentially, we are there to promote and actively develop the uptake of digitalization within the automotive sector to improve productivity and competitiveness. And that's probably, as we come out of COVID, that's probably more important than ever. And it's a key element of the Automotive Council's digitalization mission. And recently, we were asked by the APC, the Advanced Propulsion Centre, to develop a new digitalisation roadmap on behalf of the Auto Council BEIS. BEIS are the Department for Business, Energy and Industrial Strategy. And if you're interested in that roadmap and haven't seen it already, you can find it on our website. So moving on to today's webinar. This is the second one in our trilogy of After the Possible digitalisation series. The first one was 2 weeks ago, and that was about Project Optima, and that involved GRM Consulting, Red Bull Racing and McLaren, and it talked about the use of digitalisation techniques in composite development. And moving on to today's webinar, so this is today's focusing on innovation within auto machine learning to help us start to predict failures in vehicle service, and it's a bit of a David and Goliath story. So I guess you're all familiar with Ford. So Ford Motor Company, part of the fabric of the UK auto sector for probably over 100 years now. Big investor in UK R&D and indeed globally, and doing some really interesting things in connected vehicles. But you're probably less familiar with Kortical. So Kortical are a data science SME based in London. And here's an interesting statistic. So last year in 2020, more money was invested in tech startups in the UK than France and Germany combined. So we think that's a huge success story and something, it's a massive resource we should be exploiting. And many of these startups, including Kortical, are actively engaged and pretty successful in some of the more data-rich industries, like banking, fintech, and pharmaceutical, but probably less so in automotive. And that's something we feel quite strongly about at IDE. So as a sector in automotive, we're becoming more connected than ever. And as a result of that, we're generating exponentially increasing amounts of data, probably more data than we know what to do with. And we think tools such as machine learning can be massively powerful in harnessing that data to speed up and almost redefine how we develop products, get them to market faster, better, cheaper, and also how we manage those products in service and improve our customer experience. And the webinar today is just one good example of that. So presenting to you today will be Russell Andrews from Ford and Alex Alling from Cortical. So before we move on to that, I need to do the obligatory housekeeping. So Alex, if you could just share the housekeeping slide. There we go. So at the end of the session, we'll run a Q&A. So we'll invite you to ask questions. If you have any questions during the webinar, please pop them into the Q&A box. We try to keep the Q&A interactive and relatively informal. So where possible, we'll invite you to come live and you can put your question directly to the panel. The chat function will also be enabled. And there you can chat to the panelists only or to the other members of the audience. We will be recording today's session. And the purpose of that is to make it available to those who couldn't attend the webinar. So the recording and the PowerPoint presentation will be available on our website. And also would invite you at the end of the webinar, if you have time, we'd welcome any feedback. So there's a short Mentimeter survey. So if you can, please partake in that. So that's probably enough from me. I'll now hand you over to Russ Laddens from Ford to get into the meat of the webinar.
Yeah, good morning. Thank you, Peter. So I am Russ Andrews. I'm the current model commercial vehicle quality manager for Ford. As Peter said, Ford has been in operation for nearly 120 years now. It is a household name in the automotive industry, operates in 77 countries and sells cars and trucks in over 200 countries. As a commercial vehicle quality manager, I understand it's an unfortunate fact that our vehicles and components can and at times do break down, and the frustration of this experienced by our customers is very evident. And so it's my department's role to understand and resolve those issues as fast as possible to support our customers, whether they're fleet operators or single owner drivers. A commercial vehicle is their lifeblood and a tool of their trade. So with the recent situation globally with shutdowns and stay-at-home orders, we've seen a boom in last mile delivery and home delivery services. So when we engaged with the Cortical and the IDE on this project to sort of potentially have a tool that would predict failure, maybe allow us to manage maintenance interventions and ultimately prevent unplanned downtime, we consider this as a huge benefit for everyone and it assists us in our goals. So that was the motivation for Ford, big company, but to join in with Kortical, as Peter said, a much smaller one in this proof of concept project. It's it's been a good journey, an exciting opportunity to develop machine learning models and identify how to diagnose vehicles with faults in a live environment. Ford has provided hundreds of thousands of lines of raw data, which Kortical was able to use and put into their technology to build different machine learning methodologies to look for and predict the potential failures of components in engines or vehicles. The results of which Alex will take you through. And these have led to some sort of business cases that Ford will review, maybe further develop and explore to their ultimate goal. Thank you.
Hello. So I'm Alex. I'm the CTO and co-founder of Cortical. So this is our presentation on the journey Russ just mentioned, where we kind of went from this raw data from the car's diagnostic systems and modems and looked to see if we could diagnose failures in advance. So the executive summary is this. We're going to show that we can predict a range of issues from applying machine learning to diagnostic trouble codes, which we call DTCs, found in car diagnostic data. Being able to do this implies that we can provide, to some extent, remote diagnostics in real time. And then for a specific issue, we then show that we can predict that failure in advance in a reasonable proportion of instances through connected modem. And so this kind of implies we'd be able to help provide predictive maintenance, part ordering, and things like repair scheduling. We do a deep dive into that business case, and we show that there's potentially a real benefit to customer downtime. So what's the big vision here? Well, the number of cars with connected modems is increasing year on year. In fact, we expect almost all cars to have modems in a not too distant future. And what does that actually mean primarily for the customer, but also for the OEM and for the dealership? Well, let's look at a few customer pen portraits. So let's look at Mark. Mark's van is his lifeline. It carries the tools he needs to be able to help his customers and put food on his table. With his previous van, breakdowns could mean days off the road, cost him dearly. His new Transit, however, lets him know if it's suspected to be an issue before the component fails. But more than that, it's ordered the part, it's booked a slot in the dealership, and something that could have been a couple of days waiting for a part to get delivered is now a repair that can happen in his lunch break, which means Mark's back on the road and he's able to do his job. let's look at a different scenario. We've got Chris and Emma, they're on their honeymoon in a remote part of Scotland when the unthinkable happens and the engine warning light comes on. And they're not sure what to do. They pull over to the side of the road, but luckily we can use ML to interpret the connected vehicle data, detect the issue, and send them a notification that it's safe to continue the journey. It's just a sensor, don't worry. And that's kind of logged in the repairs upcoming at the dealership. You know, and obviously the improvement in customer experience is in itself a benefit to the OEM. But there's other factors such as intelligent alerts, like increasing the adoption of things like the mobile phone app, which can help increase engagement and brand trust. Certain issues, especially ones that involve software, can be resolved over the wire potentially if you can detect them. We can understand and catch some failures potentially just after the production line before it's left the factory before delivery. And logistics for spare parts can be optimized, specifically kind of the last part of the logistics chain there. So, you know, the other important actor here is the dealer, who's the primary kind of face of the brand and the interaction with the customer. So, you know, for dealers, they're going to know potentially what's going to roll into the shop this week, and they can therefore benefit from appointment optimization, staff scheduling, you know, and demand planning in general. And then also, you know, they can hold less parts in their inventory because they can have a better understanding of what might fail and what they might need. So we can have a reduced inventory and just-in-time kind of part ordering. These are all visions about what might be the art of the possible. We're not going to necessarily prove any of these out, but this is just to kind of show you the universe of possibilities that that would be unlocked, you know, in a future state where we have this ability. So the ultimate vision here is you've got the customers with connected vehicles all interacting, sending us real-time data, so we can make sure the customer relationship management and dealerships are all able to act on that and give that customer the best experience possible and give that fleet the maximum amount of uptime. And from a brand point of view, you know, really show how how the customer is incredibly important. So for an example use case here is this predictive part ordering. So you're going along and on the power cycle, the DTCs are going to be sent through the modem, and us and Ford, we can analyze those and we can understand, or how likely is a given part to fail. And if that failure exceeds a certain threshold, we just go ahead and order the part and send it to the local dealer without even informing the customer. If and when the failure actually happens and the customer turns up at the dealer, this part in some cases will already be there. We'll go on to show that we can predict up on average 10 days in advance in some cases for a specific part. And so what could have been an overnight job waiting for the part to arrive is actually just a 2-hour affair that can happen in a lunch break. And I think this is kind of a powerful sort of story about how we can really have a big impact on customer downtime. So what do we need to prove? We need to be able to prove that, well, from these DTCs, we can actually predict any given failure. And then can we actually do that in advance and through the modem data? And that would allow us to do the predictive maintenance, proactive part ordering, and the proactive repair appointment scheduling. So you've probably heard of Ford, but you're unlikely to have heard of us. I'm just going to briefly sort of introduce us and give you some sort of notion of our credentials. We're a UK-based startup founded in 2016, and we're a cloud-based automated machine learning platform, which I'm going to explain slightly further because that might not be entirely obvious what that is. And our vision is to automate the boring parts of data science and leave more time to solve the hard problems. We have a platform primarily, but we do work with some visionary companies like Ford to help them understand and apply AI to their problems. So our clients include Santander, Capita, Deloitte, NHS. And the platform itself essentially condenses the cycle of data science, which comes from data to data explanation, feature engineering, model training, model evaluation, model explanation, and all the way to deployment, and kind of automates all the parts within that lend themselves well to automation. And what that actually means in a practical sense is we're reducing the cost, risk, and time of getting value from machine learning, and not by a small amount, but by a considerable amount, like in orders of magnitude. So we're talking from like weeks and years, taken from Gartner industry averages, and we see in our own POCs more like weeks and days to get to the same results. So we do work in a lot of different verticals. and some of them are quite disparate. So, for example, we're actually helping Deloitte Power automate their tax process, and this has been an incredibly successful UK Deloitte Kortical adventure, and that's actually going to hopefully become a global part of their tax business in the following years. All the way through to things like helping an NFL team improve the revenue of their marketing campaigns. So, you know, they have every week they want to fill seats in the stadium, but they don't want to you don't want to incentivize people to come with an offer that's too good if they'd have just come anyway. So we're able to use like machine learning to hyper personalize those offers and send exactly the right offer to the right person and fill the seats. And we had an A/B test versus traditional marketing, and it was a 56% increase in revenue. The most pertinent use cases to perhaps automotive, aside from the one we're talking in detail about today, are some work we did with BT, where we had they have 22,000, their maintenance partner MBNL specifically, where we have 22,000 cell towers, and you know, cell tower downtime is a huge issue. Obviously, they want to minimize that, but during the summer months, a number of them failed due to heat problems. And we're able to look at the sensor data in the cabinet and look at specifically the power usage on the smart meter. And we found that our model could actually predict about a month in advance, just from looking at differential, like inconsistencies in the smart meter electricity usage. If there was a fan about to fail, we found we could predict about 50% of these kind of heat failures in advance. And we were able to then reorganize the engineering schedule so that we could minimize downtime, and without sending out any more engineers, just keep the existing set of engineers better utilized. A huge one for us is the NHS. So there's a specific kind of blood product which only has a week shelf life, and that's a huge logistical challenge for the NHS. So we did a big, long, year-long project, which was to use machine learning and optimization to predict for all the hundreds of different varieties and combinations of blood products. So, you know, AB negative apheresis or whatever, predict these across all the different hospitals and manufacturing centers, predict both the demand and the supply side, and then take that information and optimize where the blood should go on what day, you know, what substitution should be made. And in a 6-week pilot, we were able to actually slightly increase the availability of these blood products while cutting the waste by about 50%. And we're now in the process of being the first AI production partner of the NHS to roll out in the UK. We had a bit of a delay of that given the current climate, but we hope to start doing that next year. And this is another interesting manufacturer one, where we had a US manufacturer, and they had a problem with demand prediction. They actually had an unpredictable a major customer that was a greeting card company, and they were providing forecasts of what their demand would be, but these would be way off, like an order of magnitude off. And in a project with them, we found we could predict the customer's demand better than the customer could by quite a large fraction. And what that allowed us to do was to kind of optimize this trade-off that you have in manufacturing, where you've got this need to have a delivery on time in full. So you need to have the stock there when the customer asks for it, or within a certain time of that. And you also want to minimize your stock levels. So those are two competing dimensions there. And we're able to actually reduce the amount of overstock and increase the availability of the product by using a machine learning and optimization again. And so why are we good for this particular problem? We use AI to build the models themselves. So what we end up is really, really powerful models that are very complex, and quite a lot more complex than you could possibly build, well, a human could build in the timeframes we had to do this project. And why is that important here? Because actually false positives on a scale of a company like Ford is actually a big deal. Like, we want to minimize the false positive rate as much as possible. Just a 1% increase in false positives could completely destroy the business case for some of these things. So, and actually having some of the most accurate models in the world is actually a necessity for projects like this. And so where do we fit into automotive in general? I've colored in a slightly lighter color the ones that we'll sort of be touching on here, which is the anomaly detection, failure prediction, supply chain and logistics, and warranty analytics. But there's also manufacturing optimizations. That's kind of looking at more up to the production line level. How can we map from production line characteristics maybe to failures in this case, and so understand and optimize the settings there. Sales forecasting, which is obviously pretty universal to most businesses, but we've got quite a lot of experience in that and doing it really accurately. Engineering optimization, so that's going even further up beyond the production line to actually kind of engineering and design, and understanding potentially, you know, things like, oh, if I add these features to the car, how much will that expand our production line by? You know, how much will the cost be? Is it worth it? Interesting and hard questions like that. And then we've got process automation, which is again a kind of generic like sales forecasting, but that means taking back office operations and just using AI to do them in 90% of cases. So reducing the amount of you know, essentially process you have behind the scenes. Okay, so now to the POC. The structure is a three-part structure. So we've got a first part, which is this real-time diagnostic piece. So that's not saying can we predict in advance. They're just saying, given the DTCs that we have, the diagnostic trouble codes, and given that some attributes about the car, can we actually look at when we've got a claim by a dealer and look at when we've got these codes going off? Can we guess at what the claim was going to be? So that was the first problem we set for ourselves. And then what we did is take that to understand out of the universe of parts, which ones made sense to focus on. And we focused on a key one for the second part, which is the predictive maintenance, which was using the modem data. And so that was to looking at the real-time time series data, where you've got a power cycle in the car, and it will send any diagnostic trouble codes through the air, and they're sort of logged in the database. So we're able to see over time, could we predict these failures, and could we actually predict them in advance? And then the final part is a business case around that. And that's, yeah. So the data really is key here. And as Russ mentioned, there's hundreds of thousands of rows of data involved. So this, the static data we had was this dealer diagnostic tool, ETIS, we're going to call it. And that's essentially when a car goes into the dealership, they'll plug in a special diagnostic machine, and that will produce a bunch of these DTCs along with some other information. So we're able to have that for cars, and we can match those cars to sales and warranty claims. So we can see, okay, so this car went into the dealer at this point and it had these trouble codes, and then that dealer made this claim. This is how we could start to train the model to associate these codes with the claims. And then finally, we had this a huge amount of this connected vehicle data, which is again, this is what's been sent through the air from those vehicles that are active and have a connected modem, which is quite similar to the ETIS data, as we'll sort of see. But it has slightly, there's obviously cost to sending stuff through the air, so there's less variety of data there slightly. And how does this all sort of fit together? So the first POC is really joining on VIN and day. So vehicle identification, like looking at, for a given day, what were the ETIS DTCs looking like, and what was the claim made, combining that to do our real-time diagnostics piece. And then the second part is taking the same warranty data, but instead to connected vehicle data. And then what we did was group by VIN and did a 21-day rolling window of unique DTCs leading up to that day across all days in that vehicle's lifetime, and then train a model to predict, you know, can it predict leading up to a failure if there's going to be a failure. So that's the kind of part two, predictive maintenance. And then the part three, the business case, is kind of bringing all that together. So basically what the data we had was this DTC data, but also kind of fixed attributes like the model year, production date, and details around the engine, and things that you would know just from a sort of a lookup table, and not real time is the essence of what I'm saying here. So there's kind of quite a few data science challenges to overcome, which is kind of, you know, first, and what I'm going to do here is sort of just take you through the process of solving those, and then we'll kind of get onto the more domain specific stuff. So we've got our platform, and this is kind of what it looks like to solve this in our platform. So this is kind of like detecting, first of all, you want to sort of look at the data set and detect missing and incomplete data. So in this instance, it's like finding what the most important DTCs are, and are they relating to the kind of failures that we expect them to be? And importantly, do we have enough examples of each failure type to build a model? And often the answer will be no. There'll be like a long tail of infrequent failures, so you'll only see them once or twice. So this is all about understanding that data set and filtering it down to the ones that are salient and have enough examples that we can actually do some modeling. Then there's something called feature engineering, which is like taking that raw data and transforming it into a way that makes it easier for the machine learning to sort of solve the problem. So an example in this particular case is that we found that the set of unique DTCs actually, you could solve that really well as an NLP problem, which means a natural language processing problem. So we found some of those algorithms developed to understand human text, worked extremely well at understanding the relationship between DTCs. And we treated the DTCs as words in like a sentence. And then we had a traditional kind of encoding for the rest of the fields. And then another huge part of this is like model selection. And as I mentioned, this is sort of where the platform is really important, because, you know, what model do we use? You know, how do we encode the data? It's actually that's in itself a kind of problem you can solve with machine learning, because you can try a set of parameters, you can try a certain model, you can try kind of encoding, and then see, well, what's the score from that? And what if we tweak this? Does it make the score better? That's like a machine problem. And actually that's one of the key drivers to how we can get a really, really, really accurate model, is because we're letting the machine learning itself figure out how to configure the machine learning to solve a given problem. So what we'd do is let it run for, in this case, tens of thousands of actual models till it converges on a really, really accurate one. And that's like a process that would take months of human labor. And then the other important thing is obviously model validation. So in this case, we want to understand, do the results from the model actually make sense? Do they look right? And we can do that both inside the platform, but we'd always have a test set held outside just to double validate, and would run our results, run our predictions across that, and see, you know, does it see the failures we expect to see and get them right? And how often does it get it right? And then actually, there's another set of tests which relate to the business case, because you might actually have a high accuracy, but that also increases your false positive rate or something like that. And false positive rate in this instance is a huge factor. So that whole business case test is another layer of model validation we needed to do. And then there's the kind of deep dive model explanation. So we can explain on a row by row basis, like why the machine learning models made the decisions they did. And so we can then take that back to forward and say, like, okay, we've got this this is the failure type we saw, these were the DTCs. Does that make sense? Are we got our mappings correct? Then we can discuss those anomalies with the domain experts and really iterate until we're solid that we've got a grasp of the domain language. And it's really important that all of this can be run from code as well. So that's super important for things like version control and review, but also for like rapidly iterating and testing. So the whole platform, we can just run it from code. All right, cool. Sorry. So the first part of the piece we're going to look at is the real-time diagnostics piece. This is mapping from DTCs observed in the ETIS sessions to warranty claims made. So we firstly joined our warranty data to our vehicles based on bin and day. So we dropped any rows where the claim wasn't on the same day as the ETIS observation, just to make it simpler. Luckily, we had a lot of data, so we could just easily do this. We appreciate that's actually simplifying the problem somewhat, but we sort of cover off the how far in advance piece in the second half of this. We'll filter out claims that aren't relevant. So we were interested in specific kinds of failure based on the teams who were talking to in Ford, and who they had understood these problems. So we didn't really want to stray outside of that. We'd split our data into training and test sets, build thousands of models automatically, and then take the best model and evaluate the results. So this is an important part of the data science process, is this notion of training and test. So the training set is where the model's got all these, it's got the outcome and it's got the DTCs, and it's asked to try and build a relationship between the two and understand what outcome leads to what DTCs. The test set is how we then evaluate how well that model did. We can't show it data it's trained on, because it could know the answers just by remembering. It doesn't prove it's learnt anything. And in this particular case, we were splitting it by VIN, vehicle identification number, and by time, because we didn't want for the models, for example, to learn that this particular car has a propensity for this failure. So it's not telling us very much about how well it can predict that failure in general. It's more like how well can you recognize a car. So what we did was train it on training set A and test it on test set B. And then if we can apply our AutoML and go and have a cup of tea. But in this case, this took several days, but we've got 18,993 models to kind of get to before we sort of saw the score converge. And I'm just going to sort of bore you with some technical terminology we're going to use throughout the rest of this, which is precision and recall. And precision is to say, when we say something's broken, how often are we right? Or you could also say the inverse of the false positive rate. So if you've got a precision of 1, you've got no false positives. You've got a precision of 0.5, 50% of your guesses will be wrong. Recall is the opposite of that. It's like, of all of the failures available for X, how many did we identify? So if you've got a recall of 1, you identified all of the problem in the data, but you might have made a whole bunch of false positives along the way. So recall is really important because it says how many of these failures would we actually catch. Precision is really important because it's like how many mistakes would we make in catching them, if that's clear. This is some example results. So from the test set, we're able to sort of understand for a whole set of issues how many would we actually find the recall, and then how many false positives would we make. And you can see for some of these, the precision is actually 1, so there's no false positives. But the important thing is also that the recall in of itself doesn't tell us much. We also need to know how many of these issues actually exist in the wild, because obviously if that issue only occurs 5 or 6 times, it's not going to be a strong business case to pursue all the way through to predictive maintenance. So we looked at survival analysis for this, which basically looks at things like, obviously the historic failure rate for that part, but how many cars are out there with that part? When was that part made? Because different parts, the failures get fixed over time on the production line, and how long are we actually in warranty for? Because obviously claims aren't going to happen after the warranty date. So using this, we can actually understand the total number of claims we expect to see for each part. And then what we were able to do here is actually isolate on the y-axis, on the x-axis, we've got the recall times the number of predicted issues. So that's basically telling us how many we'd expect to find given this model. And the precision is telling us how many false positives would we expect. And you can see out here on its own is the part that we then pursued into the modem part of this, which has a good level of, a low level of false positives, but also a huge number of, not huge, but like enough issues in the wild that it makes it worthwhile looking at this. So from part 1, we showed that we can predict some kind of failures from just the DTCs and ETIS data. We showed that, so a subset of these parts have a viable business case, but the next step is to do this in advance on modem data. So this is slightly more complicated because you've got a time element. So what we wanted to do was essentially first join on warranty data based on VIN and day, but we also applied some time-based feature engineering to this, which we'll go into detail on. We then also obviously removed the unsuitable observations. Things like, is this observation after the claims be made? So therefore, obviously unrelated to the issue. Splitting into training test sets, feature engineering, and again, thousands of models. So in a very similar way, we split our data by train and test set. We dropped any VINs that appeared in the test set from the training set. And then, we performed this kind of time series feature engineering, which is essentially grouping, like running a rolling window of 21 days along the history of the connected modem. And we're creating an observation. We split the vehicles into 2 groups, a group that had failures and a group that had no failures. And for the group with failures, we created this window right up until the point of failure. And then that point of failure was our positive observation. And then for the VINs with the cars with no failures, we just ran this window along the whole time series from the connected modem. So what we'd expect to see is hopefully our model finding more failures in the positive group and less in the control group. Again, we said about building lots and lots of models, but didn't have to do very much because it sort of happens automatically. The real time spent here was in validating our assumptions and the feature engineering and really understanding the data. And actually, that's the sort of place you want to be spending the time rather than fiddling with models. So actually, that's where all of the power of kind of machine learning happens, where the connection between the sort of domain experts and data scientists. So the results. So what we were able to show is that actually, we can predict this particular failure from the modem. Depending on where we set the threshold, we'll get a different level of recall and false positive rate. So you can have the threshold lower, and we'll catch more failures, but you'll also make more false positives, or you can have the threshold higher, in which case you'll obviously catch less of the failures, but you'll also make less mistakes. And another really, really interesting finding was that the results we got were a completely different model on the connected data were pretty much equivalent to what we saw from the ETIS data. So we saw a recall of about 0.4, which is about the 39.28, and we saw a false positive rate of about 6%, which is again roughly similar. What that kind of implies is, you know, some of these other issues might also be viable at detection through the modem, and it's kind of what we expect because the data from the modem is pretty similar to the data that we get from the ETIS session. So that was kind of the expected result, but it's nice to kind of have some proof point there. So the other issue was, well, how far in advance can we predict this? So we thought that the average distance in advance was about 4 days. But the actual technicalities of this issue mean that in some instances that issue can, the way it fails can happen either through a drawn out process of corrosion or through an instant change in the properties. And if that happens, there's obviously going to be no way to predict it. So if you kind of filter out all of the times when it happened instantly and just look at the subset, which was still quite a large fraction where it didn't immediately fail, we found that the average days in advance was actually 10 days, which is quite a decent amount of warning. And so, you know, how do we then apply this? So this is where the classifier threshold comes in again. So depending on how confident we are that this is an actual failure and not a false positive, we might want to act differently. So for example, if based on just the, you know, very, very low confidence, we might still want to plan on logistically on a high level, because even if we've got 20 cars with, like, you know, 70% chance of part X failing, over the across 20 instances, that's going to average out at basically that. So you can make these logistical decisions on a kind of like the low confidence scores. And maybe when you get a bit more confident, you'll still be wrong, but it's at this point it's worth ordering the part. So the cost of shipping that part to the dealer compared to the cost of the customer downtime, that equation starts to balance in favor of shipping the part. And then maybe when we're starting to get even closer to the point of failure, the confidence has got up another notch, we might want to get the dealership to actually reserve a repair slot. And only then, when we got the real almost certainty of failure, would we alert the customer. So we really alert the customer, or potentially we don't alert the customer, and they just, when the vehicle fails, they call the dealer who's already got the part and already got them a slot. So depending on how well we can how low we can make that false positive rate depends on, you know, how actively we alert the customer. So the final part of this really is the business case around predictive part ordering. So this was, if you remember, the scenario where you've got a breakdown that happens, but we've detected it beforehand and we're able to ship a part to the dealership. And really, the uptime hours saved here is based on you know, the customer not having to spend the normal amount of time to wait for the part to be delivered. So this involves looking at the total population to check, you know, how many failures are actually out there to find, what's the cost of the shipping, and how many hours to ship the part. And based on that, we can sort of plug these into our business case equation and find, you know, these points will represent different classifier thresholds. So we can say, well, what's the optimal point? Where are we getting the most saved value for customers in terms of uptime saved, without too much cost? And that all depends on, you know, what the various values of these properties are. So if there's lots of failures to find, you know, it means that your recall accounts for more. For example, if the cost of shipping is quite high, it means the cost of being wrong is more larger. So you want a lower false positive rate, for example. So if we just take an example, typical, you know, theoretical customer journey, you know, they're going along, the warning lights on, they get a limp home mode, or, you know, just totally fails at the roadside. They'll then call the dealer for a service. They'll leave their vehicle at the dealer. We'll start the clock. You know, the dealer runs diagnostics. The dealer orders the part and waits for the part. and then the customer has to come back the next day or a few days later to collect that part. And we're projecting that you could, in fact, in some cases, do it more like this, where the car sends the DTCs to us and to Ford. We sense that part is over the failure threshold exceeds what we set as our threshold. So we know, okay, it's of a certain likelihood that it's worth now ordering the part. So that part gets ordered potentially before the customer even knows there's a failure. And then when finally the car does have the warning light or does enter limp home mode or fails at the roadside, and they then subsequently go to the dealer, that dealer at the very least already has that part in stock, but potentially also has booked a bay and things like that too. And we can see that for the part in question, that potentially was a downtime of 2 hours versus an overnight repair. So in summary, we've proved that we can predict a range of issues from applying machine learning to DTC's redundant ETIS data. So this real-time diagnostics case looks like it's viable in some instances for some parts, obviously to be proven out more. And I think for a specific issue, we've gone some of the way to proving that we can, in some instances, predict failures in advance, or at least it very much looks like it from the tests we've done so far. And worthwhile enough potentially to take this a step further and do a live pilot of some kind, potentially. Because that kind of demonstrates that if that is true, we'd be able to provide some elements of maybe the predictive maintenance or predictive part ordering or repair scheduling. And kind of another important, but maybe less glamorous result is that when we looked at the business case for some of these things, there is actually quite a nice business case there, especially because of, customer downtime is a really valuable, costly thing. And, it's kind of many faceted. So it's, reducing it's very good all round. And, kind of to wrap this up and bring us back to the sort of vision, we've got this connected sea of vehicles that's growing year on year out. The number of sensors in those vehicles is only going to increase, as is the resolution of those sensors and the amount of data that gets sent through the air and bandwidth on the modem and so forth. So we expect this to just be more and more useful and help more and more customers as models tend to get better with more examples. And you'll find some of those issues that didn't have enough examples before, suddenly because we've got a large sea of data, we're able to actually make more sense of them and start to predict those. And we really think that, done right, this could elevate the customer experience and reduce cost and reduce downtime kind of in an increasing way, year in, year out. And this is just kind of one example of how machine learning can be applied in automotive, improving people's lives in this case, as well as just optimizing the business, which is, it's really nice to have an application that's going to have some tangible benefit. But obviously there's quite a few other ones we sort of touched on, and we're finding it as a company, we've really enjoyed working with Ford, and we thought they were great. And we're really interested in this industry, and we think there's potentially loads more really exciting use cases out there. So we'd love to have a chat if you're interested, or you just want to learn more about what we've done here. So I'm aware I'm about 7 minutes early, I think. So I'm handing over to the Q&A now. So thank you very much. Appreciate your time. And yeah, please let us know or get in touch if you have any questions. So obviously we have some questions now. So I'll leave myself sharing, and I guess Peter.
Yeah, great. Thanks for that, Alex. That's really interesting. So yeah, I guess hopefully if some of the audience aren't too familiar with what auto machine learning actually is, I hope this at least gave you some insight into that murky world. And also I think it's worth bearing in mind, this project was a 4-month activity. So I think it was, as you can probably see, it was pretty intense for the partners involved. It was a real sprint of activity, but I think it does show, machine learning isn't the panacea for all problems, but when you apply it in a real targeted, specific way, you can get some immediate results. So let's move over to the Q&A. We've had quite a lot of questions, so we may have time to cover them all if we can. The first one is, I think, from Carsten Dirk. So Carsten, if you're able to come live and ask your question.
Hi, Peter. Carsten here. Thank you. Not sure if the question goes to Alex or Russ, but with the vision of reducing the downtime for the customers by identifying the components which fail, are we also looking at the surrounding components which could fail during the repair? So for instance, your example around the PDF, the particular diesel filter, if that fails, it could go to an exchange, which means the screws needs to get cut off so you can take it out of the exhaust system and then the new one placed in. So are we then looking at the screws as well? Or if we come to a static regeneration, normally some OEMs advise to do an oil change as well, because it doesn't work as in the same way. So are these kind of attributes from mechanics when they are exchanging parts being considered as well to have repair components which could break during the repair activities itself?
Yeah, that's a very good question. That's a very interesting one too. I'll attempt to answer the first part and maybe hand over to Russ for some of the technical details there. But essentially, what you find with machine learning is we don't come in with any assumptions. So it can actually, if in that case the diesel filter that failing did actually lead to other failures, the model is actually just able to pick that up as well, and it can. What we're able to show in fact is that those exact kind of insights are actually come out of the data without us knowing. So we saw some stuff where a particular issue was actually caused by another issue, and we were able to find that relationship without knowing anything about the domain itself, or with our journeyman knowledge of engineering, not knowing what these acronyms meant. We were able to say, hey, does this make sense, and then validate that with Ford. So yeah, in essence, it's a great point. I think that's something we should look at factoring in, certainly, and to some extent it is already factored in kind of in terms of the probability of the failure. I'll hand over to Russ if you've got any other comments, Russ.
Yeah, with depending on how we would take this forward into a real life situation, if the model was able to predict a failure and it sent the information to Ford, who would alert the dealer and said, this is a DPF change, the dealers who would be receiving the information would know that what's involved in a DPF change in that example. So if we've got single-use bolts that are required, they could have that prepared and ready. If it was something that they had to order in, and we've got this on a 2 or 3 days in advance, they would be able to look and say, okay, well, this diagnostic code has come in, or this is what we believe to be the fault within here. So anything that's that predictive forward, the dealer would, if we took it to the nth degree, the dealer would have the information ready to handle that whole vehicle. If there are failures that are common but not related to the failure, which I think, having read your question, do we get other accidental failures? But if they're common, well, again, the dealerships would know what is a sort of normal common failure in that part, and maybe have those parts ordered as well.
Well, yeah, I think from my point is to factor that in. What it sounds like, Russ, you're referring to the experience of the mechanic and the dealership. So if I take another example, the camshaft sensor has to get exchanged, and now the screw, by untightening the screw, it shears off, it breaks down. So if that repeatedly happens, that could go into the database and associated with the failure of a camshaft sensor, please order that M5 screw because it's likely to shear off.
Yes,
Absolutely.
Yeah.
Okay. Interesting. Yeah, that's just, if that's been considered, that would be probably a help for the people in the workshop, because yeah, having worked myself 6 years in the workshop, it's just a repair of an ABS sensor, will be done in half an hour. All of a sudden the screw goes off and you haven't got that particular screw to hand, and then you're there and ordering that material now, and then the vision goes out the window, unfortunately.
Yeah. Yeah, understood.
Okay, yeah, thank you for that, Carsten. We've had another couple of questions from James Williams. I'm not sure if James is able to go live. Are you there, James, or I think you may have to draw off the call? If not, I can ask on his behalf. But not sure James is there. So I think, yeah, this is a good question. So his understanding from the presentation was that the automl techniques, they rely on historical data. So as the industry is sort of rolling out zero emission powertrains we're having to, both battery electric vehicle and hydrogen, how effective is the approach where real world data sets are limited in size? So we maybe haven't got that bulk of historic data. And the second part also is, what is the general acceptable rate for fault detection? So I think that one's probably to the both of you.
Yeah. Okay. Well, I'll go first if you like, Russ, again. So the first part of the question was around the data set, and yeah, you're completely right. If we don't have the training data, you can't build a model. The assumption would be that there's a sufficient number of similar parts between even an electric vehicle and a normal vehicle have a lot of parts in common. So there would be that, but also the fact is that the whole fleet isn't going to be electric overnight. There will be a transitional period during which time training data will accumulate. So couple that with the fact that you don't have to have that many issues to build a model correctly. You're not in the realms of kind of Google-sized big data here. We can do quite a lot with quite a small set of examples, and by a lot I mean there might be a business case, which kind of talks to the second point, which is what's the acceptable rate. Well, depends what you're doing, and quite if you're actually going to go and call the customer up and say, oh, you've got a fault, you want to be incredibly certain that the thing's going to fail. How you balance that equation from a customer experience point of view is probably more of a business decision, but that's really what we'll give. What the output tends to be from models is like a probability of the thing happening, in this case the failure, and then the business logic needs to go around that. So if it's just like reordering the logistics, then that again, that's a decision where you probably do want to act on that, like in all cases, because if you've got a population of cars, then it will be right on average. So I maybe asked that question. There was a kind of a slide on it. I'm not sure if you probably asked that before we got to that, but I'll hand over to Russ again.
Well, I think you covered most of it. I mean, this was a proof of concept to see whether or not predicting data predicting failures from modem data was possible. So as we roll out with BEVs and zero emission vehicles, they will have their own modems and an own set of issues that come out from that. If we have the models there to follow a similar type of modeling that we've done for these particular issues that we found here, then there's no reason why we wouldn't be able to sort of take that forward. It's around size of data set. The other thing, of course, that happens in vehicles quite often is you start to see trends appearing. So whilst we get if we were seeing this type of information coming in and there's a trend, well then OEMs start to react to those trends very quickly anyway, and other things come into play to protect the customers.
Right, thanks for that. I think we've just got time for a couple more questions. So we had I think one or two questions from Faisal. Faisal Sheikh, are you able to come live, Faisal?
Yeah, can you hear me very well?
Hi, Faisal.
Yes.
Hey, Alex, how are you doing? I have a question relevant to operations for OEM. For example, in a machine, they have historical data of machine failures. So if we are going to do AutoML, I mean, what kind of data they would need to get out, or is this kind of a specific format? And sometimes we see the data is from different applications like ERP and SAP or something. How we will able to manage these kind of things?
Well, luckily we've got an excellent partner in Ford who handled a lot of the sort of low-level data aggregation and stuff. So we got relatively clean data sets, and I appreciate that's sort of dodging the question, but what you've touched on is actually a very big blocker for a lot of machine learning proof of concepts, because if it costs a lot of money to get that data out of the various different backend systems and join it into one sort of data model, that can add a lot of cost. So that's something to consider when you're going to approach this. If you talk to the right people in the company, often that can be a massively reduced cost because they'll just know how to do it, or they might have even done it before, or they might just have built similar models. And as companies become more machine learning mature, the general trend is to get things into a more centralized data store, because there'll always be interesting POCs throughout the businesses, and those companies want to be doing stuff with the data. So I'm hoping that is a trend we'll see over time where, more and more companies won't have the same issues of data in strange formats or in closeted systems, but I'm sure it will remain an issue for the immediate future. But yeah, it's a good question. And I don't know if you've got anything to add on that, Russ.
No, I think that the realms of that question was definitely within what you're answering there, Alex.
Yeah, fair.
Thanks, Alex.
Okay, I think we've just got time to squeeze in one more good question. That's from Naveen. Are you able to come live, Naveen?
Hello, can you hear me?
Hi.
Hey, hi, Alex. I think mine was in the similar vein to Faisal's question, was the data cleaning and the data prep. How easy was it, or how easy is it to automate this process? And especially whenever you mention about feature engineering as well, the better your features are engineered, the easier or faster it is to get the right model for it. So I suppose, yeah, that is, I mean, I think you've kind of answered it to a certain degree. How easy is it, and how much can you automate that process, I suppose, both for cleaning the data and also for feature engineering?
Yeah, good question though. I think that is slightly different, to be fair. So just the aspect of kind of getting that data into a common format or a common data model, which is one element of the sort of process, which I don't really think you can automate that because it's so domain specific. You need to know what data sets you have. But then going forward from there, what you mentioned, things like feature engineering or data cleaning, that's actually kind of handled by our platform. So it just works out the best way to deal with missing values and things like that. And I mentioned that we encoded DTCs as a sort of text field, and we actually automate the parameters of that transformation. So we're searching for all the different kind of ways you can build that NLP and looking at which ones solve the problem the best. So in that case, in that instance, we were lucky to be able to automate the feature engineering as well as the model training, which does add kind of power to the model because you're going to get the best representation with respect to the model you've got.
Yeah, I suppose if let's say if you're crossing domains, so if let's say if you've got DTC codes and you've said you've coded them in or classified them as an NLP problem, but if let's say you've got various different types of data interacting with each other as well, so you've got a string, you've got numbers, you've got integers, how would that be able to be automated as well?
Yep. So like in this instance, we had exactly that. So we had the DTCs as text, but we also had categorical and numeric fields, which were like the car attributes. So we just have that. You can just throw that on the platform and it works out, and it combines those encodings before it does the machine learning.
Cool. Okay. No, brilliant. Nice one. Thanks.
Awesome.
Okay. Thanks for that. Yeah, and I think we're just about coming to the end. So thanks particularly to Alex and Russ for presenting. As I mentioned, there's a quick Mentimeter survey after this if you do have time. We're always looking to improve how we run these events, so your feedback is much appreciated. And just to remind you, the final webinar in this trilogy is in 2 weeks' time. I think it's 2 weeks yesterday, so on a Wednesday. And that one is Project Air Force. So that's involving University of Bradford and Jaguar Land Rover. And that's looking at, again, sort of advanced digital modeling and how we can model driver behavior in this instance to optimize control system strategy in both conventional combustion engine and hybrid electric vehicles. So that one again is in 2 weeks' time, and you can sign up to that on LinkedIn. So I think that brings us to a close. So again, thank you everyone for attending. It was really good to see attendance today. And for your questions. And for those questions we didn't get to answer, we will take a note of those and we'll definitely get back to you directly. So I think we're drawn to a close now. So thank you again and enjoy the rest of your day. Bye now.